So far we have talked about creating a one sample interval for the mean using a z-distribution and then a sample proportion, right? We were looking at confidence intervals for population proportions. So today, right, we're going to talk about what if the population standard deviation is unknown. So it says up to this point, we have calculated confidence intervals for a population mean, mu, when sigma, right, which is the population standard deviation, is known using the formula, right? So we had the sample mean minus the error, sample mean plus the error, where error was, right, we saw sigma, which was the population standard deviation, and we saw z of c because it was the normal distribution. Now, in reality, it is rarely the case that the population standard deviation is known when the population mean is unknown. In this section, we will learn how to calculate confidence intervals for one population mean when the population standard deviation is also unknown. So again, if we don't, right, we will always know a standard deviation. It just may not be the population standard deviation. It may be a sample standard deviation. So when we don't know, right, the population standard deviation, the best way to estimate it is with your sample standard deviation, or S, right? So we have S for our sample standard deviation. Just like when we don't know the population standard deviation, we estimate it with X bar, right, which is the sample mean. This changes the confidence interval formula in two ways. So the first one is when you no longer know the population standard deviation, you cannot use it in the formula. Where you see the population standard deviation, or sigma, in the confidence interval formula above, you will replace it with its estimate, the sample standard deviation, S. The second thing, it says when using S to estimate sigma, right, so you were using the sample standard deviation to estimate the population standard deviation, you now have more variability in your confidence interval estimate. Instead of only attempting to estimate one quantity, or the population mean, we are now trying to estimate two quantities, the population mean and the population standard deviation. This increase in variability changes the distribution from the standard normal distribution, or a z-distribution, to the student's t-distribution called just the t-distribution. So the confidence interval formula for one population mean when your population standard deviation is unknown, you'll actually notice this piece here looks exactly the same, right? Because it's not taking into account really the sample standard deviation and the critical value, just with E. Right now, if I look at what actually E represents, we can notice, right, now we see S and we see T of C. So we are seeing a slight different notation right now because we don't know the population standard deviation, and now we're using a T distribution. So we now need to talk about the student's distribution, or the T distribution. The T distributions, there are infinitely many of them, are very similar to the Z distribution. They are bell-shaped and symmetric about zero, just like the Z distribution. What makes the T distributions different from the Z distribution is their spread. There is more variability in the T distribution than there is in the Z distribution. This increased spread, or increased variability, is due to the fact that we are now estimating both the population mean and the population standard deviation, rather than just the population mean, as is the case when we using the Z distribution. The reason there are infinitely many T distributions is that as the sample size n increases, the spread of the T distribution starts to decrease. So this happens because as we take a larger and larger sample size, S, or the sample standard deviation, becomes a better and better estimate of the population standard deviation. So just sort of a summary of what happens. As n increases, so as your sample size increases, your sample standard deviation becomes a better estimate of the true value of your population standard deviation. Now, as S gets closer to the true value of sigma, the T distribution decreases in spread. Thus, for larger sample sizes, the T distribution starts looking more and more like the Z distribution. So in fact, as if your sample size, right, if you think of going to infinity, the T distribution sort of approaches the Z distribution. And because the T distribution decreases in spread as the sample size increases, there is a different T distribution for each sample size. Each particular T distribution is defined by its degrees of freedom. You'll see it as df. The number of degrees of freedom is equal to the sample size minus 1. So again, I'll just rewrite it. So degrees of freedom is your sample size minus 1. We can use the invert t key on the calculator to find t values corresponding to our required area and degrees of freedom. So our inverse t is set up so it's like our area, and then we have our degrees of freedom. Now, what I want you to do is to see if you have this function on your calculator. So some of the older calculators do not have it. So where we're going to find it is we're going to hit our second button, and we're going to hit the vars. Now, mine has it. Mine's number 4, the inverse t, so I am good. If your calculator has it, then you're good. If you are missing this, you probably have the inverse norm, and then it goes the t PDF. Then you're going to have to program it into your calculator. So I will have a video attached in the course that you can do this, but if you're just watching this in general, if you Google inverse T, like TI-83, it usually will pop up some videos on how you can program it into your calculator so you can actually go through and do this step. So if you don't have this inverse T in your calculator, now's a good time to pause it and go ahead and enter it in, and then we'll start back with example 1 in our next video.